Now it is visible. Now it's visible.
Yes. Yes, yes. Now it is. I think now I'm able to see the participants as well. Okay. Fine. I start from zero again. So the radar is actually the emerging or very reliable sensor as compared to any existing sensor. I will compare the radar also with other sensors in the next coming slides. What we can do with the radar is actually we can measure the dynamic parameters of the radar. So dynamic parameters in the sense we can very accurately measure the range of all the targets. So in front of the radar are all the objects of interest so in front of the radar. And then we can also accurately measure the velocity of all the objects or all the dynamic objects that are moving or the dynamic objects which are moving. Then apart from range and velocity, we can also tell where they are located with respect to the radar, how many degrees left side or how many degrees right side or how many degrees above or how many degrees below. So I think I think somebody switched on the microphone. Probably they can turn off their microphones. Yeah. So then I think the range estimation and the velocity estimation are very essential to understand, to be able to understand how to estimate how to measure the breathing rate and heart rate. So first I will start with the range estimation. So before getting onto this, if you position, there are different ranges classification of the radar. So we have the short range radar that usually goes from 20 centimeters to 80 meters. Then we have the medium range radar that goes all the way up to 160 meters. And we have the long range radar that goes all the way up to 250 meters. Then we have the video range up to 80 meters. Usually video goes up to 30 meters actually. So 30-40 meters, but up to 80 meters also we do get the image. But the objects of interest in the total frame occupies very small portion. So it will be very difficult to actually classify the objects in the frame. On the other hand, when you compare with the ultrasound, so those are very short range sensors, so operate in tens of kilohertz, for example, 48 kilohertz. So that goes only 3 meters. So usually in the automotive industry, those are used. So I have shown the automotive context, but actually the radar is very well used in the very much used in the industrial applications where small vibrations are monitored, small movements are monitored, or security surveillance. But on the other hand, it has a very reliable application for the medical industry where we want to do the measurements by non-contact, means by measuring the heart rate and breathing rate. Right? When you position the millimeter wave range in the entire spectrum, the millimeter wave entire electromagnetic spectrum is shown here. The millimeter wave range actually spans from 30 gigahertz to 300 gigahertz. Then we have terahertz on the top, then we have IR there, then we have visible. Then high frequency, we have X-rays there. Then most of the wireless communications happen actually below the millimeter wave range here. Then we have FM here and AM here. So 30 to 300 gigahertz is basically classified as the millimeter wave. When you use such range, the antenna size actually becomes very small. So it is very easy to design the systems with very compact size actually. When your antenna size becomes so compact, then it's very easy to design very compact and highly portable are integrable devices actually very easily to be able to move one place to other place also very easy. Also to be able to place for measurements or to do anything, that will become much easier. When you look into the physical properties, actually the generation and the spatial resolutions, actually coupling size and propagation aspects and all. So it is generated by electronic means. The physical millimeter wave is actually generated and it will be transmitted. And we all the time will be looking into the reflections. The spatial resolutions will be on the order of millimeters. Actually, this is millimeter wavelength. So that's why it is actually spatial resolutions will be on the order of millimeters. And coupling antenna is actually packaged on the PCB. Or we can just print the antenna with the metal. So that is also another thing. Then it actually propagates through walls and boxes and soft materials, like if somebody has a dress on them, right? So that actually penetrates through soft materials. So that will be no problem. So huge applications in automotive sector and industrial sector. And there are two bands actually used. I did not show here. 60 to 64 gigahertz is very popular, and 77 to 81 gigahertz is very popular. As I told, what we can do with the radar is actually to be able to measure the range, velocity, and angle of arrival of multiple targets that are actually in front of the radar. So range in the sense, the shortest range from the radar to the object. That is what is called a radial range, the shortest path that can be drawn between the radar and the object. If there are 10 objects or 10 targets, then we can measure those ranges very accurately. On the other hand, the fundamental limitation is if these 10 objects or 10 targets are radially located. For example, here it is shown the radial range. It is the shortest distance between the, if this plus sign is the radar, then if target is located here, then it is the radial range, the shortest path between the radar and the object. So that's the radial range. If there are 10 targets are actually equidistant from the radar, then radar will not see them as a different targets or different objects. Radar sees them all same target, even if there are 100 which are equidistant, because when you transmit the signal goes to all the targets in front of all the objects, then it reflects back at the same time. So that is the reason. So that's a fundamental limitation, right? So there's a physical limitation. Then velocity can be measured. Then I'll come back to the range resolution when the time comes. Then the main advantage of the radar is like majority of the things are done with the RGB camera or at least some sort of imaging thing. But the radar is non-imaging class when it comes to these one-dimensional applications. If you do not use the array of transmitters and receivers, if we use the array of transmitters and receivers, we can get the image. So radar also can be classified as the imaging device as well. But when you use a limited number of resources, a limited number of transmitters and receivers, this is a non-imaging device. But on the other hand, this is very robust to environmental conditions like fog, dust, and smoke, and operates pretty well in very low light conditions, no light conditions, independent of light actually. It also penetrates the soft materials such as the dress and soft material, plastic enclosures and all. So all these things. So there are huge advantages when using radar. It is also a long range sensor as compared to many imaging devices or many imaging sensors. Okay. So huge number of applications starting in the medical domain to hand gesture recognition or automotive driving and industrial and robotics and communication systems and civil engineering, parking aids, object detection, medical application actually. So this is how the medical application is done actually. The radar, the object of interest, the person of interest will be sitting in front of the radar. We transmit the signal towards the chest where heart is located. Then heart movements and the chest movements are actually captured to be able to measure breathing rate and heart rate. So this is what we are going to look into. But to be able to look into this one, we need to have the basics of how the radar operates and what sort of parameters we can measure. I'm not getting into all these details. I quickly move on to the fundamentals of the radar. There are quite many applications there. So usually traditional radar is a very big radar. It is used actually to be able to detect the targets and precisely, and also track the targets and trajectory prediction, and all these things actually were used using the radar. But when the radar became very small in size, when we moved on to the millimeter wave range, and the radar became very easily available for civilian applications such as automotive, industrial, and medical applications. So that is the reason now it is much easier. So this is also non-ionizing radiation, so that there is no harm when you use the millimeter wave signals towards the body. So that doesn't harm, that doesn't knock out any atoms or any elements in the compound structure, in the structural part, so that we will not get any ionization in the body. When the moment it becomes ionization, then our body exposed to the radiation, then